This is Chapter 2 of Chemistry and Measurements, Section 7, Density. So most of us have a pretty good intuitive understanding of what density means. It's sort of the heaviness or lightness of an object. So for instance, we know that if something is less dense than water, it'll float in water, things like cork and ice. And if something is more dense than water, like aluminum or lead, then they'll sink if you put them into water. So the goal of these slides is going to be to learn how to calculate the density of a substance, to learn really what density is in a scientific sense, and then to use the density to convert between the mass of a substance and the volume that it occupies. So density compares the mass of an object to its volume. It's really the ratio of the mass to the volume. So a certain mass of a pure substance will occupy a certain volume. This is what the equation looks like in words. A lot of times you'll see it written out as density D equals mass M divided by volume V. Okay. The density of solids and liquids is typically in grams per centimeter cubed or grams per milliliter, which is the same thing because a centimeter cubed equals a milliliter. But gases are much less dense, so they are typically measured in grams per liter, which is a much smaller unit. So here we have a table with the densities of some common substances listed, and you can see here in the middle we have the density of water, which is 1.00 grams per milliliter. So if you have a milliliter of water, it'll weigh 1 gram. If you put a beaker onto a scale and you pour water in it until the scale reads 1 gram, you'll find that you've measured out 1 milliliter of water. You also see these substances here and here, which have densities of less than 1, and those are things that are going to float in water, right? Cork, ice, those things float. Even other liquids like gasoline or oil, if you mix them into water, when they separate, those will tend to float on the surface because they're less dense. Okay? And then we also have these substances down here and here, which have densities greater than 1. So these are things that are going to sink in water. Okay, if you put a piece of aluminum or copper into water, obviously it'll sink to the bottom, right? And now on the right-hand side, we also have gas densities. Okay, and you can see that some of them are less than 1 and some of them are greater than 1. So you might be fooled into thinking that these gases here float in water and these gases maybe sink to the bottom of water. But that would be very unusual behavior for a gas. Okay, so what's really going on is that we have a different unit in this column, grams per liter, right? I mentioned that gases are typically measured in the grams per liter unit. So in order to compare any of these densities to the rest of the densities in the table, you would have to take that number and divide it by 1,000. So the density of carbon dioxide, for instance, is not 1.96 compared to water, it's 0.00196 because you have to divide it by 1,000 in order to get it to be grams per milliliter. Determining the density of a solid is relatively straightforward. Density equals mass over volume. So if you have an object, you just need to determine its mass and then determine its volume and divide one by the other. So for a solid object, it's very easy to get the mass. Typically, you would just put it onto a scale or a balance of some sort and then just read what it says. Okay. In this case, you assume all of these digits are significant figures. So this zinc cylinder has a mass of 68.60 grams. For the volume, there are, generally speaking, two ways to determine the volume. The first is if you have a regular shaped object, like a cylinder or a sphere or a cube. And in those cases, we know from mathematics that there's a simple formula that relates the dimensions to the volume. So for a sphere, for example, you can just measure the diameter and use the diameter or the radius to determine the volume from the formula 4/3 pi r cubed. For other shaped objects, though, we don't have any simple formula like that. And so we can use a technique that's called displacement, measuring the volume by displacement. So in that case, what you would do is you would take some amount of water, a known volume of water in a graduated cylinder, for instance, like this, and you would put your object that you're trying to determine the volume of into the water. The volume of the object is going to push out of the way the water around it. And so it's going to cause the volume of the water to increase. Okay? So you're going to see the volume go from the initial volume on the left-hand side here to the final volume here on the right. This difference in volume is called the displaced volume, and it's equal to the volume that the object takes up. right? The volume of the water has gone up because it can't fit into the space where the object is. So this is how you can determine the volume for an irregular object. In this case, the volume was initially 35.5 milliliters, and after placing the zinc cylinder into the graduated cylinder, it rose to 45 milliliters. Now, there are two assumptions that are being made here. One is that the object is completely submerged underneath the surface of the water. Okay, if any part of it is above the surface of the water, then it's not displacing its total volume, and so the displaced volume will be less than the real total volume. Okay. The other assumption is that the object is completely uniform in its density. It's not filled with holes or any other substances. It's not a composite that has different substances or different densities at different parts of it. Okay. If this zinc cylinder, for example, were hollow, it would be displacing a volume of water much larger than the volume of actual zinc that there is. Now that we've taken these measurements, we can determine the density. We already know that the mass of the object was shown on the scale, right, 68.60 grams, so that's very easy. But to determine the volume of the substance, we did the measurement by displacement. So now we just have to do a little bit of simple arithmetic, take the final volume that the water level rose to, subtract the initial volume, and we end up with the displaced volume, which is the volume of the object that we put in. So that is how you determine the volume of the object, and then you can put that into the equation for density. You have mass from the scale, the volume from displacement, 68.60 divided by 9.5 gives you 7.2. The other thing to keep in mind about this is two significant figures in this answer because the volume has two significant figures where the mass has four. Right? So we keep the one with the lowest number of significant figures. The volume has only two significant figures because even though the volume measurements individually have three significant figures, when you subtract them, you only keep the same number of decimals as they both have. And so the tens place disappears when you subtract 35.5 from 45, and you end up with only two significant figures in that volume measurement. Here's another example, which we'll go through quickly. It's exactly the same. This time, they don't even say that we're putting the piece of metal on a scale. They just tell us it's a 48.0 gram sample of metal. We know that the initial volume of the water is 25.0 milliliters, and then after they add this object to the water, we end up with a volume of 33.0 milliliters. So putting this into the same equations, we measure the volume by displacement by taking 33.0 milliliters and subtracting 25.0 to get 8.0 milliliters. And then we take the mass from the problem, which is 48, and we divide it by 8.0 milliliters. That gives us a final answer of 6.0 grams per milliliter. Again, keeping in mind significant figures. So again, as long as you know the mass and the volume of a substance or object, then it's rather trivial to calculate the density. You just take the mass and you divide it by the volume. So you can think about this as a simple formula, right? Density equals mass over volume. But it's also often useful to consider the density to be a conversion factor that allows you to translate between the mass and the volume. Okay, that's why we're studying density in this chapter on conversion factors. Here's an example of a problem where that way of thinking would come in useful. So the problem statement is John took 2.0 teaspoons of cough syrup. If the syrup has a density of 1.20 grams per milliliter, and there is 5.0 milliliters in 1 teaspoon, what was the mass in grams of the cough syrup? Now, you could think about this as a problem that requires two separate steps, right? Where first you need to convert the teaspoons to milliliters because that's what the density is measured in. And then once you have the volume in milliliters, you can put that into the equation density equals mass over volume. You have the density, you have the volume, you rearrange the equation to solve for m, and that gives you your answer of mass m in grams. That's one way to do it, and that's perfectly fine if you want to do it that way. But it's, like I said, useful to think about density as a conversion factor where you're converting a known volume into a mass. And in that case, it makes a problem like this a little bit easier because you can sort of do everything in one process, just chaining together these conversion factors. So let's see how that works. So the first step, again, is to state the given and needed quantities. This is virtually always the first step that we take in a problem like this or in many other problems in this course. So we're given the volume of the syrup, right? We want to know what the mass of the syrup is. So in some way, we had to convert from volume to mass. That means we're going to need to use density. The problem is the density that we're given is 1.20 grams per milliliter. It doesn't tell us grams per teaspoon. So before we can use density, we do need to convert teaspoons to milliliters. So that's step 2, right? Writing a plan to calculate the needed quantity. So we see here to go from teaspoons to milliliters, we need this factor that tells us how many teaspoons are in a milliliter or vice versa. And then to go from milliliters to grams, then we're just using the density as, again, another conversion factor. Okay? Rather than plugging it into an equation, we're just going to be looking at it as a conversion factor. So if both of these things are conversion factors, then we'll need equations for them. Okay? So on the left-hand side, you have 1 teaspoon equals 5.0 milliliters. That's directly from the problem statement. And so that gives you these two conversion factors, 5 milliliters per teaspoon or 1 teaspoon per 5 milliliters. And then if we look at density as a conversion factor, we can say that 1.2 grams equals 1 milliliter for this particular type of syrup. Again, using density as a conversion factor means that it's a context-dependent conversion factor, that it will only apply to this problem or to problems involving this particular type of cough syrup. And so the conversion factor that we get from there is either 1.20 grams per 1 milliliter, which is really just the density, or it's the reciprocal, the inverse of the density. So now that we have our plan and we know the two relationships or equations that we're going to need to use, the next question really is which of the conversion factors we choose, right? Because each equality that we came up with, each relationship, leads to two different possible conversion factors, and it's very important that you pick the right one. So in doing a problem like this, I like to set up the equation the way you see here, right? First, we start with the thing that we know that we're trying to convert, right, which is 2 teaspoons. We're trying to convert 2.0 teaspoons, the volume of syrup, to the mass of the syrup. Grams of syrup is what we need on the end, because that's what it's asking for. What is the mass in grams? And so since we know that we needed two conversions, two relationships, because that was the plan we came up with, we can include two conversion factors like this, and I like to write them as sort of blank ratios multiplied by the initial measurement. So the reason that I do this is because then we can begin to sort out which units need to go where, right? Remember, the units in your mathematical equations need to cancel out and work out to be the same on both sides. So if you start with the teaspoon unit here in the initial measurement, well, your first conversion factor has to cancel the teaspoon unit. So that unit has to go on the bottom so that it will cancel properly. Okay? And if you want to end with grams of syrup as your unit, well, then your last conversion factor has to have grams of syrup in the numerator of the conversion factor so that that will be left. Okay? And then the other thing is that whatever unit goes here in the first conversion factor has to be the same unit here in the second conversion factor so that that will cancel. Okay? So the first relationship that we need is the relationship between teaspoons and milliliters. Okay? And we saw that on the last slide, but again, it's given here in the equation. 1 teaspoon equals 5 milliliters. So that means we're converting teaspoons to milliliters. And then the second step is the conversion using density, 1.20 grams per milliliter. So here we have grams on top. So again, on the bottom, we're going to have milliliters, which again matches the unit at the top of the first conversion factor. Now that we have the units in the correct place so that they cancel out, right, you can see teaspoons cancels teaspoons, milliliters cancels milliliters, and then we'll be left with grams of syrup. And now that the units are in the correct place, then we can just fill in the numbers as we saw. We can choose, make sure that we're choosing the correct conversion factor. So for the first one, 1 teaspoon equals 5.0 milliliters. And for the second one, 1.2 grams of syrup occupies a volume of 1 milliliter. And so we know that we've put these numbers in the correct place. We don't have to ask ourselves, do we divide by density or do we multiply by density, right? That's a common question that students ask when they're approaching problems like this. Well, am I supposed to divide or am I supposed to multiply? The fact is, I never remember it that way. And when students ask me that, I actually can't answer it right away because I have to set it up this way to make the units work out. So once we have this, then we can just do the math, right? 2.0 times 5.0 divided by 1 times 1.0 divided by 1 gives us 12 grams of syrup. So the answer to this question is that 2 teaspoons of cough syrup weighs 12 grams. And then the last thing that we need to be aware of are the significant figures, right? So our initial measurement of the volume was given to 2 significant figures. Our relationship between milliliters and teaspoons is given with 2 significant figures for the milliliter unit, and then the 1 teaspoon is considered to be exact in a relationship like this. The density is given to 3 significant figures. 1.20 has 3 significant figures, and then again, the milliliter we consider to be an exact number. So 2 significant figures times 2 significant figures times 3 significant figures gives us an answer that's to 2 significant figures. And so that's why we round this to 12 grams. Here I have another question, right? An unknown liquid has a density of 1.32 grams per milliliter. What is the volume in milliliters of a 14.7 gram sample of the liquid? So again, there are 2 ways to do this. We can take density equals mass over volume and just plug our numbers in, right? So the density is 1.32 grams per milliliter, and that equals the mass, which is 14.7 grams, okay, divided by the volume, which is what it is we're trying to find. And so we would need to do some algebra to solve for V to get the answer. Okay, this is simple algebra that you should be able to do for this course. There's many questions in this course where you'll need at least this level of algebra. So it should be trivial for you to solve this for V and say V equals 14.7 grams divided by 1.32 grams per milliliter. And then you would get your answer, right? But it's also possible to do this, again, as a conversion problem, where you start with the mass of the sample that you're talking about, and you use the density as a conversion factor, right? The density factor is a conversion factor here. So if we do it that way, we get this. We have the relationship between volume and mass. 1 milliliter equals 1.32 grams of liquid, which gives us either this conversion factor or this one. In other words, we're wondering whether we need to multiply by the density or divide by the density. But rather than just memorize which one it is, we can work out the units. So we take our initial measurement of 14.7 grams and we multiply it by a conversion factor that has grams in the denominator and milliliters in the numerator. And that will allow grams to cancel out and it'll leave the milliliter unit, which is what we're looking for, right? That's what it asks for right here in the problem. So once we do that, we know now that the grams have to be on the bottom and the milliliters have to be on top. So that means that we have to put the 1.32 here and the 1 milliliter here. So we're taking 14.7 and we're dividing it by 1.32. Okay, so the answer is we're dividing by density in this case. But I didn't need to memorize the particular case, I just worked out the units. Okay, and then again, we can look at the significant figures. In this case, both of the inputs have 3 significant figures, and so our answer is also going to be measured to 3 significant figures. The last part of this density section is specific gravity. And specific gravity is really just an alternate way of looking at density. It measures the density relative to the density of water. So in other words, the specific gravity is the ratio between the density of a substance and the density of water. And you can see that here in this equation, right? Specific gravity equals density of the sample divided by the density of water. Now, in the unit of gram per milliliter, this is a very, very simple calculation because the density of water in grams per milliliter is 1.00. So any number divided by 1 is just the same number. The only thing that happens is that the unit will cancel out because you have a gram per milliliter unit in the numerator and a gram per a gram per milliliter unit in the denominator. So those will cancel out, and you'll end up with something that is a unitless quantity. It expresses just a pure ratio. So something with the exact same density as water is going to have a specific gravity of 1. Something with a density less than water is going to have a specific gravity less than 1. Something with a density greater than water will have a specific gravity greater than 1. Now, it sounds trivial again because we're used to measuring the density of water in the unit grams per milliliter, where water is just 1. But the sort of advantage of specific gravity is that it has the same specific gravity no matter what unit system you're looking at, because the unit disappears. So even if you're measuring the density of your sample in some other unit, then you just convert the density of water to that unit and you'll get the same specific gravity. Or you can convert everything back to grams per milliliter and get the specific gravity that way. In practice, it's even simpler than this, because since we almost always use grams per milliliter, then as long as you're given the density of a substance in grams per milliliter, then the specific gravity is the exact same numerical value. It's the exact same number, but it just doesn't have the grams per milliliter unit. Okay?